Ever get that feeling like you're just itching to know what's coming next in tech? You know, that next big thing, the thing that's going to completely change how we use our devices.
Absolutely. It's
Yeah.
exciting to think about.
Well, today we're diving into something that really is on the bleeding edge. Thermodynamics computing chips.
Oh, interesting.
So picture this, devices that are not only insanely fast, but also incredibly energy efficient, all because they're using heat. You know, the stuff we normally try to get rid of to actually do the computing itself.
Right.
Pretty wild, huh?
Yeah, that sounds like something straight out of science fiction.
I know, right?
Yeah.
We're going to break down the basics of these chips, talk about why they're so important right now, and then we'll get into some of the ways they actually work.
Awesome.
And of course, we can't forget about the challenges because there are always challenges with new tech,
Right, right.
but also the amazing possibilities these chips could open up for the future. I'm really excited to unpack all this.
Me too. Let's get into it.
All right, so first things first, let's talk about the traditional computer chips that we're also used to. You know, the ones that power basically everything we use. What's going on inside those things, and why do they always seem to be heating up?
Okay, so traditional chips, they rely on these tiny little things called transistors. Basically, they're like super fast switches that turn on and off.
Okay, I think I remember learning about those in like high school physics or something. Vaguely.
Right, exactly. And it's that on and off, that's what creates the ones and zeros, the binary code, the language of computers. But here's the thing. Every single time those transistors switch states, every time they flick on or off, they run into a little bit of resistance.
Huh.
And you know what resistance creates.
Let me guess. Heat.
You got it.
Yeah.
Heat. It's like when you rub your hands together really fast, they get warm.
Yeah, okay, I see that. Friction.
Exactly. It's basically electrical friction at a microscopic level.
So the more we cram onto those tiny chips, the more heat they generate and the bigger the problem, right?
Absolutely. And we keep wanting more power, more speed, more everything. So we keep packing more and more transistors into smaller and smaller spaces, and the heat just keeps building up.
Which leads to a whole bunch of issues, I imagine.
Oh, yeah. I mean, first of all, there's a limit to how densely you can pack those transistors before they just melt.
Makes sense.
Plus, all that heat makes them run slower. And then we have to come up with all these complicated cooling systems, which take up space and use even more energy. It's a whole mess.
So that's where the idea of thermodynamics computing comes in. It's like, instead of fighting the heat, what if we could actually use it?
Exactly. It's a
I just
complete
wondered.
paradigm shift. We're talking about leveraging the very thing we've been trying to get rid of, thermal energy, and using it to do the computations themselves.
Okay, but how? How does that even work?
Well, this is where we get into some fascinating physics. Thermodynamics, at its core, is all about how energy moves around, how it changes forms, and how it relates to concepts like work and entropy.
Entropy, that's the one that always trips me up.
Yeah, entropy basically refers to disorder in a system, like how much randomness there is. So in a regular chip, think of all those electrical signals bouncing around, creating heat, kind of chaotically. That's high entropy, lots of disorder.
Okay.
With thermodynamics computing, the goal is to design systems that are incredibly good at channeling that randomness, that inherent disorder, into a more organized form that can be used for computation.
Like taming the chaos and making it do something useful.
Exactly. It's like, imagine a rushing river. If you just let it flow freely, that's a lot of wasted energy, right?
Yeah.
But if you build a water wheel, suddenly you're harnessing that energy to do something productive.
Mm-hmm.
Thermodynamics computing is kind of like that. It's about creating those water wheels inside the chip itself.
Okay, that makes a lot more sense. So it's about using clever design, both in the materials and the overall architecture of the chip, to basically make the heat do the work.
Exactly. And there are even some experimental ideas about using temperature gradients, differences in temperature across the chip, to drive logic operations without even needing extra electricity.
Wow. Okay, so we've got the basics of what these chips are and how they kind of work, but why are they so important right now? You mentioned energy efficiency, sustainability, and scalability. Let's start with energy efficiency. Why is that such a big deal?
Well, think about it. Data centers, the places that store and process all the information for the internet, for cloud computing, for AI, all that stuff,
Yeah.
those things guzzle down a crazy amount of energy. Like seriously huge amounts. They account for a significant chunk of global electricity consumption.
Right.
In fact, if you put all the data centers together, they use as much power as some entire countries.
That's wild. I had no idea.
Yeah, and the problem is that energy use is only going to go up. Our demand for data is exploding. Everything's moving to the cloud. AI is getting more and more powerful. It's not slowing down anytime soon.
So if these thermodynamics chips can actually make a dent in that energy consumption, that would be a pretty big deal, wouldn't it?
It would be a game changer. Imagine if we could even cut the energy use of data centers in half. That would be like taking a huge number of power plants offline.
That's pretty mind-blowing. And of course, that ties directly into the whole sustainability issue.
Totally. We're all trying to figure out how to reduce our carbon footprint, right?
Yeah.
In the tech industry, well, we have a big role to play in that. Making computing greener is a huge part of the solution. Thermodynamics chips could be a key piece of that puzzle.
So we're talking about potentially running these massive data centers or even just our personal devices on way less energy.
Exactly. We could run those complex AI models or those blockchain networks that everyone's talking about using a tiny fraction of the power they currently use.
That's exciting. And then there's the issue of scalability, right? I know we've been talking about Moore's law for decades, but it sounds like we're hitting a wall.
You're right. Moore's law, which predicted that the number of transistors on a chip would double about every 2 years, it's been amazingly accurate for a long time. But we're running into some fundamental physical limits.
Meaning what?
We're getting to the point where those transistors are just getting too small. We're talking about sizes where the weird rules of quantum mechanics start to really mess things up. So shrinking them down any further, using our current methods, is becoming unbelievably difficult and really, really expensive.
So we can't just keep making things smaller forever.
Not with the way we're doing things now. And that's where thermodynamics computing offers a new path forward. It's a totally different way of thinking about computation, so we're not limited by those same old constraints.
Okay, I'm starting to get the picture. So we've talked about why thermodynamics computing is such a big deal. Now let's dive into the how. You mentioned two really interesting approaches, stochastic computing and spintronics. Can we start with stochastic computing? I have to admit, the idea of using randomness for computations sounds kind of counterintuitive.
It does, doesn't it? But here's the thing. Physical systems, especially at really small scales, they're naturally noisy. There's randomness everywhere. So instead of trying to eliminate that noise completely, what if we could actually harness it? That's what stochastic computing does. It embraces that randomness. Instead of representing data with those perfect ones and zeros, it uses probabilities.
Probabilities.
Yeah. So think of it like this. You have a stream of random bits, like flipping a coin a bunch of times.
Okay, so like heads is 1 and tails is 0.
Exactly. But instead of caring about each individual flip, we look at the overall percentage of heads and tails. That percentage, that's how we represent the data.
So it's more about the likelihood of something being a 1 or a 0 rather than a definite yes or no.
You got it. And since thermodynamic processes are inherently noisy anyway, this kind of probabilistic approach actually fits really well.
Okay, that's starting to make sense. It's like turning a weakness, that inherent randomness, into a strength. What about spintronics? You mentioned it uses the spin of electrons. So what is spin exactly, and how can we use it to compute?
All right, so this is where we get into the quantum world a little bit. Electrons, they have this intrinsic property called spin. You can almost imagine it like the electron is a tiny spinning top with a north and south pole, and that spinning creates a magnetic field.
Okay, so we're not just talking about the electron's electrical charge anymore.
Right, in spintronics, we're also using that magnetic property, that spin. So we can have spin up, which might represent a 1, and spin down, which might represent a 0. And the cool thing is you can flip that spin, change it from up to down or vice versa, using way less energy than it takes to move a bunch of electrons around in a regular circuit.
So it's like a much more efficient way of switching between those ones and zeros.
Exactly. Plus, spin-based systems, they interact with heat very differently compared to our usual electronics. Manipulating that electron spin, it can generate way less heat than moving electrical charges around.
So that's where the energy efficiency comes in.
Exactly. And we're already seeing some really exciting applications of spintronics in things like memory storage.
So both stochastic computing and spintronics, they're both about looking at information and computation in a totally new way.
Right. It's not just about pushing electrons around anymore. It's about finding completely different ways to represent and process information, ways that work with the inherent randomness and the thermal energy in these systems, not against them.
It's really mind-blowing stuff when you think about it, but let's be realistic for a minute. There must be some major challenges to making all of this actually work.
Oh, for sure. There are some big hurdles to overcome. One of the biggest is the material science. Building these new kinds of chips, It often requires some pretty exotic materials, stuff like graphene, which is super strong and conducts electricity incredibly well, or topological insulators, which are really weird materials that are like an insulator on the inside but a conductor on the outside, and quantum dots, which are these tiny little semiconductor particles that have all these crazy quantum properties.
So the challenge is actually making these materials.
Exactly. We need to be able to produce them in large quantities and at a reasonable cost. And that's not easy. It takes a ton of research and development.
And then there's the actual manufacturing process, right? I imagine building these chips is a lot more complicated than what we're doing now.
Absolutely. The way we make chips today, all that super precise equipment, it's been designed and refined over decades. But for thermodynamics chips, we might need entirely new methods, new machines, new everything. That's a huge investment.
Yeah, I can see that being a major obstacle. And finally, there's the software issue. I'm guessing our current software isn't really designed to run on these kinds of chips.
You're exactly right. The entire way we write software, all the programming languages, all the algorithms, they're based on the way traditional computers work. But with thermodynamics computing, we might need entirely new programming paradigms.
So we're talking about a lot more than just tweaking a few lines of code.
Oh yeah, it's a complete rethink. We might need entirely new programming languages, new tools, everything. It's a huge challenge for the software world.
So it sounds like we're still a ways off from having thermodynamics chips in our smartphones and
For
laptops.
widespread adoption, yeah, probably. But the good news is there's a ton of research and investment happening right now. Governments, big tech companies, everyone is pouring money into this field.
That's encouraging. It sounds like people really believe in the potential of this technology. So let's say we do overcome all these challenges. What kind of future applications are we talking about? What could this really lead to?
Okay, so get ready because the possibilities are pretty amazing. Imagine self-driving cars that can go way farther on a single charge because their chips are super energy efficient.
Okay, that would be huge.
And think about AI. Right now, training those massive AI models takes an incredible amount of energy. But with thermodynamics chips, we could potentially do it using a fraction of the power.
So we're talking about making AI way more accessible and sustainable.
Exactly. And that's just the beginning. We're talking about entirely new kinds of devices, things we haven't even thought of yet. Like imagine sending probes to other planets that can survive in those harsh environments because their chips are designed to work with extreme temperatures.
This really feels like the next big leap in technology, like a complete paradigm shift.
It absolutely is. It's not just about making things faster or smaller. It's about changing the very way we think about computation, working with the laws of physics instead of constantly fighting against them.
It's an incredible idea. What part of all this excites you the most?
For me, it's the sustainability aspect. The idea that we can create technology that's not just powerful, but also in harmony with the natural world. That's something I'm truly passionate about. What about you? What resonates most with you?
Honestly, for me, it's the sheer sense of possibility. Like, this is just one example of how our understanding of the universe can lead to these mind-blowing technological breakthroughs. Who knows what other seemingly fundamental limits we can break through if we just keep exploring and experimenting?
I love that. It really makes you think, doesn't it?
It does. Well, this has been an absolutely fascinating deep dive into the world of thermodynamics computing. It's clear that we're still in the early stages, but the potential is absolutely huge. Thanks so much for walking us through all of this.
You're very welcome. It's been a pleasure talking about this stuff with you.
And to all our listeners out there, keep that sense of wonder alive. Who knows what incredible technologies are just around the corner waiting to be discovered?